My name is Jidong Kang. I'm coming from Chemo Materials. Yeah, it's a federal lab in Canada. This is the work that we have done during the pandemic. Majority of the work done by my former postdoc, Waqas, and we do have a collaborator doing the surface polish for us, and Professor Kang Inal is my academic partner on this project. Aluminum silicon tan magnesium alloy has been studied extensively, but the background for this research is at that time we worked for a major automotive company, so we tried to use additive manufacturing sort of to do everything we could to make autonomous drive cars, but the concept failed after 3 years. It's not only for my project, it's for the entire concept. So the CEO of that company got fired, but we still have some results here. So we concerned about three things. One is whatever you do for additive manufacturing, I have to say that you always got internal defects, no matter how you do. And then the surface, the second thing is it's always very rough, right? If you, for a machining purpose, it's a piece of garbage. And then also, people talking about it, the heterogeneity of the material. So intrinsically, you have residual stress. So we try to deal with that, and then to see if we can have any solution for that. So keep that in mind. The material we're dealing with is really very conventional, and you probably have thousands of publications on that. But we use a different approach for the 3D printing. We use a conduction mode, so we have very compact. We got a compact rate over 99.6, something that number. So, and then here are the chemistry we use and the mechanical property we can achieve. So you can see here, we can get very high UTS, but a little ductility over there. So, but this is not the key point. The key point is, so we have a geometry. It's a kind of modified ASTM fatigue sample, but we'll be able to do both fully reversed and R.1 fatigue testing. So here are the EBSC data. As you can clearly see on near the surface, the microstructure is very different compared to what's in the center, right? That's everybody talking about it. So here's the trick. So we work with an external company called RAM. It's a small company based in the United States. They develop a chemical mechanical processing. So you can combine chemical and mechanical. So you can not only do external polish, but you can possibly do internal polish, right? So what happened there is, so this is after, before that. So because we use a conduction mode, and then we didn't do any board scanning, so the surface is very rough. I will show the results in a minute, and then this is after the polish, right? So if you must, so the surface roughness, here the average is 45 micron. Probably you never print such a rough surface, but we just want to highlight that differences. And then this is after polish, so you can get about 0.3 micron. You can do CT scan, so you can see you have tons of those defects on the surface. And then internally, you still have some of the big ones. So we also measure the residual stress, use XRD. And then here's the trick. So for the S-builds, you have some kind of tensile residual stress all the way. But after that polish, chemical mechanical polish on the surface, you get about 100 micron compressive residual stress. So we do just fatigue testing, as I said, because we use a different geometry, so we'll be able to do R-1 and 0.1. Here are the results. So for the S build, you really don't see the R ratio effect. for that specimen. But if you do that polished one, so you can see here, this is R.1 and this is R-1, right? So you can see if you take the 1 million cycle, so you can clearly see the differences in terms of the strength. So if you look at the fractal surface, and then you can put all this in together, we follow an old paper done by someone else. So you basically try to figure out if there's really a fractal toughness of that specimen. So this we put all the samples together, and then so it seems you get a K1C afterwards for all the specimens. Then you take that number, and then this is another thing. We just take a very simple approach. So you treat all those defects, internal roughness. So there are defects. So, and then you can do that. So for the as-built one, so apparently the roughness causes the defects. If you use the Murakami approach, you take the square root of the area. So, so they are dominate that. And if you take for the polished one, because they have very smooth surface, so then you potentially is highlighting the role of the defects. So we take that and then put into this equation. As I said, it's a pandemic, so we have the funding, but we cannot find people to do the work. And even we cannot do a contract, because at that time, the federal government don't allow us to contract out. But we find the literature data. So you can take all those numbers and then from the paper. So, and then you do the trick. So here, what we got here. So this is the experiment data, and this is that simple prediction. We call it the first observation from that. So this is the 5 times 9. So actually, they are not bad. So what that said is, so I hope I show you is we have a very effective polish process. Is a chemical, combined chemical and mechanical polish. So it's not only give you the smoother surface, but also we'll be able to produce a slight compressive residual stress on the surface. And it looks like that kind of compressive residual stress gives some benefit. When we tested that 0.1, so you have the 1 million cycle that the strength, fatigue strength, a 1 million cycle is improved from 94 megapascal to 212. But when you do the fully reversed one, and then you'll find that it's from 47 to 150, right? So it's a 3 times improvement. So we take a very simple approach to do the fatigue life prediction, right? So it seems the data showing, so when you have the polished sample with extremely low surface toughness, so you get probably the fatigue life is more dominated by the surface or near surface defects. And then for the as-built sample, the fatigue life is a significant controlled by the very high surface roughness. So I will stop here. Hope we can catch up time. This research was funded by the Canadian federal government during the pandemic. Then the staff in my lab contribute to this work, and also external service company doing the XRD measurement for us. And then it's really, I think, not that much report about it, the compressive residual stress in this additive manufacturing process. I will stop here, and then I hope I can open the discussion. You have questions from the audience. Thank you so much.